In this video, we are going to learn how to solve separable differential equations. So far, we have been working with differential equations without solving them, either approximating their value or trying to draw pictures of how the solutions will look like. But now we are going to actually solve them. So, given some type of differential equations that they are called separable, we are going to see a method that allows us to solve them. So, a separable differential equation is a differential equation that can be written in the following form. It's a first-order differential equation where we can say that the derivative of y with respect to x is the same as some function applied to x times some function applied to y. So it's separable in the sense that we can write those two functions and then multiply them. Equivalently, we could write the differential equation in the form some function f applied to x times divided by a function y, h applied to y. Those things are equivalent, just a matter of calling g what over h, and we'll get it. So these are the equations that we call separable, and we're going to see how to solve them. Let's see the method. Let's consider an equation written as in the second form. So we'll say that h of y multiplied by the derivative of y with respect to x is equal to f of x. And then we are going to take antiderivatives on both sides. So we are trying to find the indefinite integral with respect to x of the functions on both sides. So we'll write h of y times dy dx with respect to x is the same as the antiderivative of f of x with respect to x. Now to solve this, we are going to do a change of variable. You can see over here that we have a function y such that the function is in the integral and its derivative is there as well. So we are going to say that u is y of x, and then du we write it as dy dx with respect to x. So doing that substitution, and the next step we are going to have that the integral of h of u du has to be the same as the integral of f of x dx. So now it's a matter of being able to find what those antiderivatives are. So let's say we can find the function h such that its derivative at u gives us small h of u, so capital H is the antiderivative, and also a capital F, that is the antiderivative of our additional f. So then we will write that capital H of u is f of x plus a constant, but actually we know that u was just a shortcut for writing our function y, so h of y is f of x plus k. So what are the key points going to be here? Well, we need to be able to find the capital H function that is antiderivative of our h function. We need to be able to find the capital F function that is antiderivative of our f function. And then later on, we'll see if we can write y as, well, something else on the other side. So we'll see if we can isolate y from that function capital H. So this is the plan. Let's see one example. The differential equation we are going to try to solve is the following. dy dx is equal to 5y squared plus 9x squared y squared. First of all, we need to write it in the form that is separable. So we need to have a function of x times or divided by a function of y. So I'm going to write the right-hand side taking y squared as common factor. So we have 5 plus 9x squared multiplying it. So then with my notation from before, this will be my function f of x, and the y squared will be my function g of y. So now that we were able to separate the differential equation, we are going to write everything with y on the left-hand side. So we are going to have that 1 over y squared dy dx is the same as 5 plus 9x squared. Now we take integrals with respect to x on both sides. So we have 1 over y squared times dy dx is equal to the integral of 5 plus 9x squared with respect to x. I'm going to go ahead and solve what we have on the right hand side because that's just looking for the antiderivative of a polynomial. So that's going to be 5x plus 3x cubed. So I take derivative, the 3 will come multiplying to get the 9 plus a constant, and let's not forget this constant because it's actually important. On the other side was where we were doing a change of variables, so we'll write that u is the function y of x. So we write du instead of the derivative of y with respect to x dx. And by doing so, we'll get 1 over u squared du is the same as 5x plus 3x cubed plus a constant c. So in the left-hand side, we need a function that has derivative 1 over u squared when we take derivative with respect to u. So this is going to be minus 1 over u. So minus 1 over u is the same as 3x cubed plus 5x plus c. But we know what is u. U is, well, y evaluated at x. So minus 1 over y of x is equal to 3x cubed plus 5x plus c. And we want to isolate y, so I'm going to say that y of x is equal to negative 1 over 3x cubed plus 5x plus c. So this is the solution for our differential equation. If we wanted to check that the solution is correct, we have to take the derivative of this and check that it verifies the differential equation we are solving.